So I gave you this thing called Making Chemical Reactions Happen Faster, and I found it on Facebook. Oh my gosh. So this website, Compound of Interest, they are Compound Interest. Of Interest? I don't know. But they have a website, and they have a Twitter feed and a Facebook feed. Now, that is pretty cool. We've talked about some of that stuff, and we'll be talking more about it. Chemical reactions. But in the meantime, actually, this is a do-over slide. This is the next slide we need to start with. It says Friday to remind myself. But I thought before we look at that one, I kind of wanted to look at this one more time. So the Arrhenius equation basically looks at those two factors, the energy factor and the orientation factor, that govern how fast or slow chemical reactions occur. So K is that reaction constant, okay? And like I said, the K0 actually in your textbook uses the Arrhenius, they call it the Arrhenius constant A, capital A for A0. Now, I looked up this whole base natural logs and base E thing, and actually I posted something on Twitter about it too. We're used to the log base 10, log, log with a base of the number 10. Natural log has, and I looked it up, the value of E is like 2 point, I don't know, something, 17 something. It's a real value. And if you look at the history on natural logs, actually, the reason it's called a natural log is because there are a lot of natural relationships that just have this sort of decay or building process built into them. So a lot of natural equations have this. So, okay. So let's continue to look at this. Now we are this is the Arrhenius equation, and we're going to come up with an Arrhenius plot. I always think Arrhenius like as in Arrhenius, like wrong, but it's Arrhenius as in an A, okay? Arrhenius plot. So how are we going to plot this thing? Well, anytime, so this, if we want to get to a power, we most recently got to that power, like this is a power up here. We most recently got to that power by taking the log of both sides, and that's actually what we're going to do. Okay, so if we take the log of both sides, then what makes most sense is to go with the natural log, since we've got E there, okay? So we can say, take the natural log of both sides. Now, one of the laws of logs is if you have the product, which we do have here, K0 and E raised to this power, we can actually break it out into adding them together. Yep, and that's exactly what we're going to do here. So the natural log of K, the rate law constant, is equal to the natural log of the orientation factor plus the natural log of E raised to this activation energy divided by the ideal gas law constant and also the absolute temperature there. Now here's the cool thing, and actually I wrote it on I found my log thing and I wrote it at the bottom. I don't know. I don't think it's really a law of logs, but, and you probably already know this, but in case you didn't. You can write it on the bottom of here if you wanted to. And it goes something like this. If you are in log base 10, and you take the log of 10 raised to the x, that's equal to x. Oops, I need 2 x's. The log of 10 raised to the x is x. Similarly, when you go to the natural log of E raised to the x power is equal to x. It's not really, I was like, is that on there? I didn't see it, so I added it. Okay. Now that's significant because check this out. We have the natural log of E raised to that power, so guess what you're going to see on the next slide? It is that power. So I just thought I would kind of share that with you. Okay, so blue box means that we've kind of really arrived to something that actually we might be using. So the natural log of the rate law constant, K, is equal to negative EA over R. Now EA is the activation energy. That's very exciting for that reaction. R is the ideal gas law constant. Of course, T here is absolute temperature, plus the natural log of the orientation factor. Well, so we can plot this thing. So we're building up to an Arrhenius plot from the Arrhenius equation. So if along the y-axis, if we go ahead and plot the natural log of the reaction, the rate law constant, ln of k. Now notice this is a little bit different. We are going to run it at multiple temperatures. Multiple temperatures. Okay, and do you guys remember that I said if you change your temperature, you're going to get a different rate law constant with different temperatures? What'd you do?
I'm just making a lot of noise, I'm sorry.
Okay. So your different temperatures, you're going to actually take those temperatures, convert them to Kelvin, and take the inverse. And this is, to me, and this was the first semester, it's like I've been teaching this for a while, and I took it, of course, years ago, and then this is the first semester. Doesn't this remind you of the Clausius-Clapeyron plot? Me too. But it's the natural log, in that case, of the equilibrium pressure instead of the natural log of the, okay? You're going to have a negative slope, and then actually the slope is going to be equal to not negative heat of vaporization over R, but negative activation energy over R. Is that not cool or what? I know. Okay. So that is an Arrhenius plot from the Arrhenius equation. Okay. All right. So again, but this is a little bit different than we were looking at before, because we were doing different trials with varying the concentrations, same temperature. Now we're doing the same concentration, but actually getting a value for K at different temperatures. All right, so here we go. So let's look at an example. This particular reaction happens to be overall second order, which we aren't going to use that, but it's nice to know, maybe for something else. Here in a minute, you're going to see a list of temperatures, and at those temperatures, the K has been determined. So that's kind of nice. They did all that work for us. Okay. So we're going to use that data, the temperatures versus the K, different temperatures, to make an Arrhenius plot. And then from the slope of the plot, we're going to knock out activation energy. That's it. Not too bad. So here we go. Here's your data. Temperature in degrees Celsius, of course, one of the things we're going to have log or pro or do is to convert those to Kelvin. Okay? And then go ahead and take the inverse, and that's what's going to be along our x-axis. We're going to take the natural log of these K values, and that's going to be along our y-axis. And the slope, we can get to the activation energy. So here we go. Screenshots of log or pro or something like log or pro. This is our raw data, our temperature versus our K. I guess K, we know the units of K given the overall reaction order is second. Then we know. Yeah.
I'm sorry, I forgot to ask yesterday, but what is the 8.8 E? What is the E?
Oh, that's just scientific notation.
Okay.
So in that case, the coefficient was 8.8 times 10 to the negative fifth. Yep. You're welcome. So we need to fix our temperature, get it in units of Kelvin by adding 273. And then we need to go ahead and take the reciprocal, get it ready to plot along the x-axis, and take the natural log of the second column, which is our K. That's okay. Then we're ready. There we go. Pretty straight line, negative slope. Okay, so M is equal to negative EA over R. Units of slope will be actually 1 over inverse Kelvin, which 1 over inverse Kelvin is Kelvin. So units of slope will also be Kelvin, just like our Clausius-Clapeyron plot. Oh my gosh. Okay, so we're going to pick up that slope you saw on the previous slide, and we're going to knock out activation energy. And actually, how do I say this? I have made a mistake at this point. This is where sometimes I make a mistake working these. Okay? So M is equal to negative EA over R. However you want to think of it, I kind of think of it cross-multiplying. I can get EA is equal to negative MR. Okay? So we're ready to plug and chug. So the slope we saw on the previous slide is negative 1.1 times 10 to the 4th Kelvin. The value of R we're using is 8.31 times 10 to the negative 3rd kilojoules per mole Kelvin. Of course, Kelvin cancel. We're going to be left with units of kilojoules per mole, which is great. Our negatives cancel each other out. That's how I think of it anyway. Round to significant figures, our activation energy is going to be a positive 91 kilojoules per mole. That's your little energy barrier that we looked at on Wednesday. Pretty cool. And we're done with that problem. Another kind of version of this problem, it's the same idea. Actually, we did this with Clausius-Clapeyron relationship too, is you don't have a table. You basically are given 2 ordered pairs and asked to go ahead and knock out, in this case, use the Ks, the rate law constants that were given at the 2 temperatures, use those 2 Ks and those 2 temperatures to basically kind of do in your head or whatever what we just did a minute ago. So if we kind of think of it as taking those 2 points, throwing them up on a line, and coming up with the slope between those 2 points. Okay, so the Ks we have, we're going to have to ultimately get them to the natural log of, take natural log of them. The temperatures were degrees Celsius again. We're going to have to go ahead and convert those to Kelvin and take the reciprocal. And then if we kind of think between those 2 points of a slope, and slope is delta y over delta x. So change in the natural log of the K divided by change in the reciprocal of the temperature. That slope then, that m will be equal to negative activation energy over R. So there's more than one way to skin this cat, and I don't know, depending upon kind of what I'm thinking about, I might go about it a different way. I might draw a graph, put those 2 points there just because I want to see them, and then start kind of put ln of k over here on the y-axis and 1 over t along the x-axis. But this case, I'll kind of show you, one of the things we need to do is take those Celsius temperatures, get them to Kelvin by adding 273. And like I said, that m, that slope that we see on our Arrhenius plot, is change in y over change in x. Okay, in this case, it's if we always go with 2 minus 1, so it's the natural log of the rate law constant, the second rate law constant minus the natural log of the first rate law constant, all divided by the reciprocal of the absolute temperature of the second one minus the reciprocal of the absolute temperature of the first one. Now I'm going to go ahead and tell you another thing. This actually is on your law of logs. If you look at the second line, because you're going to see this, and we can use this to our benefit. You see how the top thing has a difference? Okay, if you have the natural log of a difference, you can kind of clean that up by taking the natural log of the ratio. So actually, you're going to see on the next slide the natural log of K2 over K1. And that's that second log. Okay, so it's just a way to clean it up. Do you have to do that? No. Are there other times when I'm going to do it to work a problem? Probably in Chem 2? Maybe. So if we go with that form, okay, I think we're ready to go ahead and plug in. Because we went ahead and had the individual Ks. Okay, there's K2 over K1. And then we had the absolute temperatures. So 1 over the second absolute temperature minus 1 over the first absolute temperature. Now honestly, like sometimes on my answer keys, I'll find what those are and then go ahead and just come up with a delta y over delta x. So there's definitely more than one way to skin this cat. But so if you kind of clean up the numerator, it comes to 2.408. You clean up the denominator, it comes to negative 0.00011. Units in the denominator are reciprocal Kelvin. That makes the slope Kelvin. So when you divide that out, you get 2.2 times 10 to the 4th Kelvin. Excuse me, negative 2.2 times 10 to the 4th Kelvin. That's your slope. That should be negative. So now we're finally going to go ahead and do what we did before when we got a slope to knock out the activation energy. So like I said, this is really easy to make a mistake here. The slope on an Arrhenius plot is equal to negative activation energy over R. Kind of flatten it out. Activation energy is equal to negative mR. And we're ready to plug in our slope. So activation energy is equal to negative times negative 2.2 times 10 to the 4th Kelvin. That's your slope times 0.00831. This is R, kilojoules per mole Kelvin. So units of Kelvin cancel out. We're left with kilojoules per mole, which is great for activation energy. Rounding to two significant figures, I get 180 kilojoules per mole. A little higher energy barrier, this one. Okay, that's that. So we'll take a look at these. These will be due on Wednesday. Makes me smile just thinking about it. Let's see. And actually, if you want to go ahead and draw an X through 56, you can, because we aren't going to get to, you need to know about half-lives in order to do that one. So you can't do that one yet, because we went out of order. 14, where did it go? And you'll see what I mean. So this is the first one. So yeah, you're going to see me work this differently. This is just like what we just got done doing. You know, they give, for two temperatures, they give the K value. And my little note, and actually this was from a year ago, I would go ahead and make like a little table where I have the temperatures that were given. I have to convert, of course, the temperature into Kelvin. No, it's given in Kelvin. Okay, so it's given in Kelvin. You have to take the inverse. You have to take the natural log of the Ks. Okay, and then I would know or think of an Arrhenius plot, and it's the change in the natural log of K divided by the change in the inverse of the absolute temperature. So to me, I would just kind of focus on this delta Y divided by delta X. That's kind of how I would do it. Okay, and once you, however you do it, once you come up with the slope, okay, then you can get to activation energy just like we talked about before. This one, there are 3 temperatures. And I think this one you need to, step A says you need to pull out Lager Pro and go ahead and put those 4 temperatures in, like we saw that example. Go ahead and convert them from Celsius to Kelvin, take the inverse, take the Ks and take the natural log of, and make your own little plot. And then A says from your plot, go ahead and come up with, using the slope of your straight line, come up with the activation energy. Like cheesy, I put a heart there next to Lager Pro. What kind of mood was I in then? Okay. And then B is a little bit different. That's still A. Blah, blah, blah. Okay. So B actually says use equation from your textbook. This is the equation from your textbook. Okay. So go ahead and do that. Should get you the same activation energy. And then C says calculate the value of K at 100 degrees Celsius. And my hint was to go ahead and use your graph. 100 degrees Celsius, you convert it to Kelvin, you take the inverse, you find it on your graph. Okay? Then you go over here and see where it intersects the natural log of K. Then you have to unpack the natural log. And I actually go ahead and give you a hint how to do that. To unpack the natural log, okay, basically you're going to take E raised to, E raised to whatever that value is, and that will give you K. So E raised to that value is unpacking to get you to K. because you're taking E,
So you
raise the natural log of K, will give you
You
K.
would just, in the calculator, you would just do E and then that
Yep,
number.
yeah, it's like,
It's like doing an inverse operation.
yeah, it's E to the X is what mine says.
Yeah,
It's my
okay.
ln
So
and
just
the.
hit E and then.
Yep.
or E to the X.
Yep. You got it. And this is the one I said don't do, and we'll see if I come back to it later. I don't think you can. First order, yeah. The T1/2 we'll talk about soon, actually next week, but T1/2 just means half-life, and we have not talked about that yet, so just don't worry about 55 yet. We might come back to it later. Okay. So back to part 3. And, yeah, part 3. I don't know if this helps or not, but part 2, remember I said I didn't want to kind of butt part 2 against part 3 and 4 because parts 3 and 4 go use graphs and part, remember, yeah, in part 1 used graphs, or excuse me, part 2 used graphs. So, but part 2 we talked about, we used what's called initial rates data, and I don't want to confuse you, we used initial rates data. In this part, basically, you're going to have just one trial, okay? It's called time concentration data. So instead of several trials, you're just going to have one trial where you have time, like in seconds, and what is the concentration at that time. Time concentration. All right. So, time concentration. Now, this kind of says that, reminds us that we have actually a couple ways of getting at concentration. We can have like a little gizmo. We can have a spectrophotometer or something that is looking at the intensity of color to get to the concentration of a reactant going down or product increasing. If you get the product that's formed, you can use stoichiometry to get the reactant that's been consumed. So there's kind of a couple ways to get to concentration of the reactant. But this is time concentration of a reactant. So what we're going to see is over time, so this is my time column, over time you expect the reactant to go down, and it will. But the rate at which it goes down will be different depending upon the reaction order. Okay? So that's actually kind of what's helpful here, or what we're observing here. So I want to focus just on using time concentration data of one trial to knock out, to understand, to assess, test for zero order, first order, and second order. That's it. So we're back to the integers again. But reaction orders don't have to be integers. And they don't have to be positive. These are all positive. But we're going to talk about a zero, first, and second order test. So starting with the zero order test. So if something is zero order, then actually we could write the rate law expression like this. And we're going to focus on, I was talking to my husband at lunchtime, he's like, well, I reminded my class. So I'm just focusing right now on reactions that are decomposition reactions, so there's only one reactant. Or that reactant could be recombining to have some sort of different conformation, okay, but we only have one reactant. So one reactant, overall first order with, or zero order, zero order. So zero order means that it has no effect. Changing molar concentration has no effect on the rate. That's cool. So anything raised to the 0th power is 1. So we could rewrite this and say that the rate is equal to K. I know it sounds strange. Even I have to scratch my head about this. So the rate is K. That doesn't mean the molar concentration is K. It simply means that the concentration is just going to go down kind of just linearly. Okay, there's no other over time. So rate, tracking the reactant A, rate is equal to, since it's a reactant, we have to say rate is equal to negative change in A over change in time, since it's a reactant, okay? And that is equal to K for zero order. So we could go ahead and use calculus and integrate that relationship. I know, that's where I'm like, what? You just have to go with me here. For those of us who it's been so long ago that we had calculus, for those who haven't had calculus yet, just make this leap for me. This is a relationship for zero order, for A is zero order. What's a relationship between? Well, it's a relationship between at any given time t, K is a constant, we have this relationship between the initial molar concentration and the molar concentration at that time. That's it. That's it. That's all this is saying for zero order. Now, we're going to rearrange that for something that we can plot. Okay. So rearranging it for something we can plot, we don't have to think too hard. We basically move the A0, which is the initial molar concentration of A, over to the right-hand side. Now, the molar concentration of A at any time t has this relationship. All right. So what can we plot? Well, we can plot along the y-axis. We can plot the molar concentration of A. And along the x-axis for all of these tests, we're going to plot time. So time is going to be the x, and then molar concentration of A is going to be, in this case, for zero-order test, it's going to be along the y-axis. So the way this test goes, and the way the other two tests are going to go, you're going to kind of see some if-then sort of thing at the bottom. So if, I don't know how you want to look at it, but if you, and I'll go ahead and put this, if you plot, and they all have time, like I said, we're going to have, this is the zero order. If you plot the molar concentration of A over time, you are going to get a negative slope. Okay, and actually up here, the y-intercept, if this makes sense to you, actually is going to be the initial molar concentration. Okay, and there's no x-intercept. Okay, but in this case, notice what your slope is going to be equal to. M is going to be equal to negative k. But this is only the case if it's zero order with regard to that reactant. Yay. And it looks like this. I guess the only thing I had here was this is the final time, T sub F. And the other thing is, notice what does this mean? This means zero concentration of A. It like totally went away. All right. So that's zero order. First order is going to be another one. And we're going to do it up to second. Actually, let me go ahead and put down here. Do you see me looking at them? Okay. I did not, and I will not expect you either to memorize these. Good, bad, or otherwise, you're getting another equation sheet for Unit 2 exam. You're going to see this on your sheet. Now, it might look like Greek, but you need to think of this, and you're going to see this. Okay, so first order. Well, if it's first order, then the rate law expression looks like this. Okay, so rate is equal to K raised to times the molar concentration of A raised to the first power. Okay, we can go ahead and just know then that rate is equal to negative change in molar concentration of that reactant over change of time, and that's equal to, K molar concentration of A raised to the first power. Again, using calculus, okay, we can actually come up with another relationship. I'm going to go ahead and put, I think I'll go ahead and put that one right here. There's actually a couple forms of this. If it's first order, the natural log of the ratio of A, the molar concentration at time t, divided by the initial molar concentration of A, is equal to negative KT. Now, we can't plot that yet, but we're getting closer. Do you remember a little bit ago when we looked at that second law right here? The second law, the log of the ratio of x to y is equal to the log of x minus the log of y. That's exactly how we're going to break that out. Okay, so that's all we're applying there, that second law. Now we're getting, actually we're ready for something that we can plot. We can plot that by now, instead of the molar concentration of A, if we take the natural log of the molar concentration of A over time versus time, again, you'll get a negative slope. And again, though, the value of that slope is negative K, if it's first order. Is my thing sneaking up? I think. Okay. So, and sometimes you're like, well, I don't know if it's straight or not. Well, that's where you can use logger pro to see if it's straight. If there's a curve to it, then that means that it fails the test. If that line is curvy, it fails the test. Okay? It fails. All right. An example of something that is first order is the decomposition of hydrogen peroxide. So H2O2 decomposing into, I think it's hydrogen, I think it's water and something. I should know this, because we just looked at it the other day. But anyway, so this actually is the natural log of the reactant. In this case, H2O2 versus time. The line is straight. It passes the first order test. Got two kinds up here. Okay. The last one, second order. Well, if it's second order, then your rate law expression looks like this. Rate is equal to K times the molar concentration of A raised to the second power. We could go ahead and get ready to integrate it, realizing that the rate is equal to negative the change in the concentration of A over the change in time, which is equal to K times the molar concentration of A raised to the second power. So now ready through the magic of calculus, okay, we can integrate that equation and come up with this relationship. This is a different marker, so I hope it's not smelly. These are Expo and that was Claridge. So here we go. If it's second order, 1 over the molar concentration of A at time t minus 1 over the initial molar concentration of A is equal to KT. All right. Well, you can't plot this one, but this one you can plot. All we did was kind of move over the inverse of the molar concentration, the initial molar concentration of A. So now when we plot that, this is the only one where we get a positive slope. So this one should give you a positive slope. And the slope, M, will be equal to K. Here, M is equal to negative K. M is equal to negative K over there. M is equal to K. The y-intercept is 1 over the initial concentration. I don't know, that might come in handy. You never know sometime. The y-intercept makes sense. That's it. So here's an example of what a passing second order test would look like. Along the y-axis, you see we're plotting the inverse of the molar concentration of A versus time. Along the x-axis, it is a straight line. Okay. It passes the second order test. So let's look at an example. All right. We don't know if this decomposition is if it's 0, first, or second order. Okay, but they ran the test once, and they went and they tracked over time the decrease in the molar concentration of NO2. And here's that data. So we have time, let's see, 1, 2, 3, 4, 5, 6 times. Okay, what was the molar concentration of the reactant? And it got less, like it should, but how does that look? So on the next slides, and actually you have a homework that you're going to want to do kind of this similar sort of approach. On the next few slides, we're going to take that list of time concentration data and we're going to make 3 plots. We're going to test for 0 order, test for first order, and test for second order. You're like, that's a lot of work. I'm like, oh, it's not too bad if you have Logger Pro. Okay. Whichever one is straight, that's going to be, it passes that test. And when we find the straight one and we know the reaction order, 0 first or second, then we just go ahead, what is K? Well, we look at the slope. If it's 0 or first, then we have to take it times negative. If it's second order, then the slope is equal to K. So here we go. The first 2 columns is the raw data. This third column is prepping it for a first order test. The last column is prepping it for a second order test. So basically, we're going to take that same time. It's going to be the same time in all cases. We just need to have something different along the y-axis. 3 plots. So here we go. This is the first plot. This is checking simply the molar concentration of your NO2 over time.
Would you automatically know that this is in the 0 order because there's change in the raw data?
No, because even if it's 0 order, it's going to change over time, but it will be
Okay.
straight, yeah.
Okay.
Yeah, because I was kind of like that too. No, you know it's going to, but yeah,
Okay.
yeah. Because it changed, it's always going to decrease over time, even if it's 0 order.
Yeah.
Yeah. But here, and actually that's what this is, it's looking at what was the change in concentration over time, and the fact that it's bowed means that it wasn't going linearly. It was, yeah. So it fails this test. Well, let's check the next test. So the next test is the natural log of the reactant. A little straighter, but not quite there. So I don't have the straight line drawn, but I'm using kind of a quadratic. So hopefully this one looks straight. Remember, for the second order, it'll be a positive slope. And if it's a straight line with a positive slope like that, that passes. So it's second order. So then the last part says, all right, it's second order, what's the value for K? What's the rate log constant? And you would just say the rate log constant is 0.537. And based upon what we've been talking about before, you know the units of K, because if it's second order, and it's actually, there's only one reactant, so it's overall second order, then you know that it needs to be, what, liters per mole time. Liters per mole time. That's it. It's kind of anticlimactic. Okay. Any questions about that? Because I'm going to take a look at the homework then. I'm going to skip the other part for now. Okay. This idea, and I want to come back to this on Wednesday, we'll kind of clean it up just a little bit, but there is a way to kind of, what do they call that, experimentally design, so that you can actually maneuver it to, if it's not decomposition or rearrangement, you can get to a second reactant. But I want to cover that later. In the meantime, these will be due also. So you'll have a long time to find your Logger Pro. Okay, these will also be due, and we'll take a look at them. Because one of these, I think it's one of these actually I pulled from you having to do, but I can't remember which one it is. So let's take a look. It's fun having that window open. It's like fresh air. Oh my gosh. Okay, so here's what it looks like. So basically, this is all together. Like 27 through 33, what the heck? But it's all one series of questions dealing with these 3 different data sets. So I have circled, there are 3 different chemical reactions, okay? And they were run once with time concentration data. And notice what you're supposed to do, number 27. It says, which of these sets of data corresponds to 0, first, or second order? And I've seen students hand this in different ways. But you have to show me somehow graphically how you came to that. So you have to be handing in your graphs.
So can we just print off 3 graphs? then,
Yes,
and then just,
yes, you can.
Okay.
You know, you don't really have to do 9. You don't have to test show me all of your failure tests. But if you want to just show me your passing test, that would be great. So one of them is going to give a straight line with the first test. One of them is going to get a straight line with the second test. One is going to be a straight line. So yeah, just 3 graphs. But to me, you have to there might be trial and error to get to those. So down here, this is what we've been talking about. This would be like your little mini graphs. Why are you smiling?
I thought they were cute too.
Okay. So 28 is, once you know the reaction order for each of your different chemical reactions, 1, 2, and 3, then you can go ahead and tell me what the K value is, or write it on your graph. Okay, you can, just on your graph, say K is equal to blah. That would be good. Let's see, number 29, was that listed there?
Yes.
Okay, 29. Okay, so 29, you can go ahead and cross off. Again, it's a half-life thing. We'll talk about half-life. It's not really complicated. But you can do 30, and I have hints on how to do 30. Okay, so 30 says, what is the approximate initial rate for whichever one you came up with second order? So my hint there is to, let's just say that number 1 was second order. So what I'm trying to say in my hint, if number 1 is second order, what initial rates means is basically at the beginning of the experiment what it was. So what my hints are trying to say is I would focus on, if this is second order, which I can't remember if it is or not, I would basically focus on this change in concentration over change in time to come up with the initial rate. That's all I would do. And 31, maybe did I say 31?
Yeah.
What's the reaction? Okay, yeah. So to me, it's similar. Notice that we've got 75 seconds, 75 seconds, 75 seconds. So there you're going to, again, kind of grab 2 here, 75 seconds, so wherever you go before or after, I'm fine either way. But the change in concentration over change in time. Okay, that's what I would do there.
I don't.
Yeah. And then, did you guys have 32? Is that listed?
Yes.
Okay. 32, I have my hint is get from the graph. So remember, you have graphs. You'll have at least 3 graphs, probably just 3 graphs, whichever one passes for 0, passes for first, passes for second. And what I would do is find 110 seconds on your graph, come up here, and then get whether it's the concentration of A. If it's the natural log of A, because it's first order, then you're going to have to take E raised to that power. Or if it's the inverse of A, because it would pass the second order, you're going to have to take the inverse of it to knock out what the molar concentration is. That's what I would do. And it's 32's not, or 32, that was 32. Okay? Yeah. Fun and games. Okay.